Hi, hello. 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 Can you unmute? Can you mute yourself, please? Can you see my screen? Hello. 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 Can you see my screen? Okay. Let us start our second class of this tutorial for thermodynamics course, and myself Thananka, and I am a PhD student at the Center for Atmospheric and Oceanic Sciences at IISc Bangalore, and today we will be discussing this second week session, live session. Sorry. Yeah, so let us start with the first question. In here it is given, we have, there is a tank. Determine the time required to fill a tank of 500 liter with water if water flows into the tank through a tape of diameter 2 centimeter and with an average velocity of 5 meter per second. And the second part is, if water leaks from the bottom of the tank at a rate of 1 kg per second, then how much more time will be required to fill the tank? Okay, so there is a tank and the capacity of the tank is 500 liter, and there is a pipe through which there is a tape, okay, through which water is being filled inside the tank, and the diameter of the tape is 2 centimeter, and the water with which the velocity with which the water flows through the tape is 5 meter per second. Okay, now we have to calculate what is the time required to fill this tank. So given volume of my container is 500 liters, and since it's standard way, we can express this to meter cube by multiplying this. Okay, so this is my volume, and what is given diameter. Yeah. Yeah. Okay, so the diameter is can you please mute yourself? It will be easier for me. Okay, the diameter is given as 2 centimeter, and this is 0.02 meter, and and velocity is given as 5 meter per second. So we will first calculate the volume flow rate, that is equal to V dot, which will be equal to area into velocity. So area will be pi by 4 into d square, and velocity is given. Okay, you put the values here: pi by 4, 0.02 whole square into 5. Okay, so you put it here, you get 5 by 4.02 whole square into 5. So this will be your 1.57 into 10 to the power minus 3 meter cube per second. Okay, so now it's a simple unitary method you should apply. In 1 second the volume filled is 1.57 into 10 to the power minus 3. You have to fill a total volume of 500 into 10 to the power minus 3. So therefore the time required will be, the time that you will require, it will be what? It will be the total volume, and that will be divided by the volume flow rate, and which will be nothing but 500 into 10 to the power minus 3 divided by 1.57 into 10 to the power minus 3, and time you will get in seconds. Okay, so the answer is approximately 318.47 seconds. Okay, is it clear? Okay, so this question has got another part. Now in the second case it is telling that water is getting leak from the bottom of the tank at the rate of 1 kg per second. Okay, the same thing. This is my case 1. I can say case A. So let me take another case. Okay, so yeah, okay, so now my case B. My case B is such that the same thing, there is a hole here in the bottom through which water is coming out at the rate of say m out. Okay, and we already know there is a rate at which it comes in, m in. Okay, now remember this m out, it is given in kg per second, so you can do both ways. You just have to make the unit same. Either you convert this m out to meter cube per second, or you convert this m into kg per second. So okay, so I'm putting this m in as it is, as I have got in meter cube per second. So my m in was 1.57 into 10 to the power minus 3 meter cube per second. Now m out, it is given as 1 kg per second, 1 kg per second. Now you have to convert this into meter cube per second. So how will you do? And we already know that density is equals to mass per unit volume. So this can also be written as mass flow rate per volume flow rate. Remember, I'm using a dashed below for volume. So from here we can convert volume flow rate as mass flow rate divided by density. So that means if we will divide this by 1000, we will get in meter cube per second. Okay, since the density of water is 1000, so this is nothing but 10 to the power minus 3 meter cube per second. Now the sum is very easy. You have a mass inflow, you have a mass in outflow. So what will be the rate of storage of this one? If my dm by dt will be what? That is my mass that is stored here. The rate of storing of mass will be the total rate of inflow of mass minus outflow of mass. Okay, and remember I'm putting all this in volume flow rate, so I can directly put it here volume flow rate also, because density is constant in both the case. So what I can write this one as, since rho is constant for all the cases, so I can write this one as what I can write as the new volume flow rate will be equal to volume flow rate in minus volume flow rate of out. Okay, so this will be 0.57 into 10 to the power minus 3 meter cube per second. Now again you have a new volume flow rate. The original capacity of this one was 500 into 10 to the power minus 3 meter cube. So what will be the time required now? Time is equals to now 500 into 10 to the power minus 3 divided by 0.57 into 10 to the power minus 3. So the answer will be 500 by 0.57. So you have got 877.19 seconds. Now remember what was the question? The question was how much more time will you require? So this is not our answer. Our final answer will be, so our final answer will be how much more time you require. Sorry, delta t is equals to t2 minus t1. Okay, what was my t2? 877.19. And what was my t1? My initial t1 was 318.47. So 877.19 minus 318.47. So you will require 558.72 more seconds to fill when there is a hole. Okay. Okay, now let us go to the next question. A rigid tank, I'm underlining the important terms. A rigid tank containing air is steered by a pedal wheel. The work input to the pedal wheel is 8000 kilojoule and the heat released to the surrounding from the tank is 5000 kilojoule. What will be the increase or decrease in internal energy of the system? So from first law of thermodynamics, what we know that Q is equals to W, which includes all the internal, external, every works, plus delta E. Okay, this is the first law of thermodynamics we know. Now in absence of the kinetic energy, potential energy and rest all the energies, this becomes W plus delta U, where U is our internal energy. Okay, so this is valid for all, and this is valid for only when delta KE and delta PE, that means no change in kinetic and potential energy involved during the entire process. Okay, this is equals to 0. Then this equation is valid for the first law of thermodynamics. Now one more thing we know, that heat added to the system is positive and heat removed from the system is negative. Now first of all, let us see our system. Our system is a rigid tank, and a rigid tank, it contains air. Okay, it contains air and there is a stirrer which stirs the air. Okay, this stirrer does work W is equals to 8000 kilojoule. Okay, and there is a release of heat from the system to the surrounding, and that is equal to 5000 kilojoule. Now first of all you have to calculate what is the increase or decrease in internal energy. Now since Q is released from the system, it is negative. Okay, and work is done on the system, so it is also negative. Now therefore if you apply here, now it will become minus 5000 is equal to minus 8000 plus delta U. Now delta U will be, I think it will be plus 3000 kilojoule. So now what we can write, that we can write that there is an increase in internal energy equal 3000 kilojoule. That means there is an increase of 3000 kilojoule of internal energy in this process. Now this is very simple. The second part, it is a bit trickier one. What is the external work? Okay, remember, what is the external work done by the system considering the air inside the tank as the system? Already this one we have considered, that's how we have calculated. That means this whole question considered air, and that's how we have calculated the first part. Now you have to calculate the external work done. If you remember in the first class, I told that work is a boundary phenomenon. Okay, this is the system, that means these walls of the container are the boundaries. Now remember, I have mentioned, I have highlighted this rigid. What do you mean by rigid? Rigid means that it will not change its shape. Okay, and it will not get any displacement. So if the boundary is not getting any sort of displacement, okay, if the boundary is not getting any sort of displacement, then the displacement work or whatever work the system is doing on the surrounding, it will be zero. That is why this external work done by the system considering the air inside, this external work done by the system is equal to zero. Let me write it again here. Okay, since it is a rigid container, okay, so no change in volume, therefore no displacement work, and therefore what was the question? Therefore external work done by the system, external work done by the system is equal to 0. Okay, is it clear? Hello? Okay. Now a stationary mass of gas is compressed without friction from 0.3 meter cube to 0.15 meter cube at a constant pressure of 0.105 megapascal. In this process, there is a transfer of 37.6 kilojoule of heat from the gas. How much does the internal energy of the gas change? Okay, what it is said, that there was a stationary mass of gas. Okay, that means this mass of gas was not moving, it was stationary. Okay, so stationary mass of gas, and its initial volume V1 was 0.3 meter cube. Now by some means, it can be by any means, okay, it is not saying that I'm doing it by piston work, I'm doing it by my hand, I'm doing it by whatever it, or blowing something. I'm just compressing it, and whenever we compress, what happens? uh, Pressure increases or volume decreases, okay, but here the compression is done in such a way that the volume is decreasing and keeping the pressure is constant, okay. So you are compressing it to a state where your volume V2 becomes 0.15 meter cube, okay. And what was your initial pressure? It was 0.105 megapascal. And what was your final pressure? It was also 0.105 megapascal, okay. That means your pressure is not changing. Now, and then it is what it is saying, that in this process, that is from state 1 to state 2, this was the state 1 and this was state 2. In going from state 1 to state 2, what happened is that there was a loss of, see, there is a transfer of 37.6 kilojoule of heat from the gas. That means from the gas to the surrounding, it went outside. So there was a transfer of 37.6 kilojoule of heat, okay. So Q is equals to what? Minus 37.6 kilojoule. Now you have to calculate the internal energy change of the gas. Again, first law of thermodynamics says Q is equals to W plus delta E. Now neglecting the entire kinetic and potential energy changes, what we can write is equals to Q is equals to W plus delta U. Now we have to find the delta U. We know Q. Now how we will calculate W? See, what is going on? Compression is taking place, okay. So W, any other things are not given, so W can be expressed as W PdV plus W electrical plus W pedal plus, and so on and so forth. There may be anything, and right now no electrical work is given, so it is 0. No pedal work is given, it is 0, but there is a displacement work, PdV work. So what we can do? We can do integration of P into dV from V1 to V2, okay. So integration, now what we will do, W is equals to integration P is what? Our constant 0.105, okay, into dV. And what is our V1? V1 is our 0.3 and V2 is our 0.15, okay. So that means what? We can write as 0.105. Remember, it is in megapascal, so we will convert this into pascal. We will convert this into kilopascal, is better, because in our case it is kilojoule, it is there, okay. So into V2 minus V1 into 0.15 minus 0.3, so which will be equal to negative of 0.105 into 10 cube into 0.15 kilojoule. So this much amount of work of compression is done on the system, okay. Now what? Now you should just have to calculate that delta U is equals to Q minus W. What was my Q? My Q was minus 37.6. Am I correct? Yeah, minus 37.6 kilojoule, and I can calculate the W, 105 into 1000 into 0.15. So this will be my minus 15.75 kilojoule. So it will be minus of 15.75, okay, kilojoule. And so what I will get here now, 37.6 minus 15.75, you will get as negative of 21.85 kilojoule. So there is a decrease in internal energy of a value of 21.75 kilojoule. Okay. Okay. So next question, an iron bar of 50 kg, it is heated to 90 degrees Celsius, and then it is dropped into a water tank of 500 liter capacity. The initial temperature of water is 20 degrees Celsius. What is the final equilibrium temperature? And you are given specific heat of iron and water are 0.45 kilojoule per kg and 4.18 kilojoule per kg. Okay, what happens? You take a 50 kg iron. Okay, so this is an iron bar and you heat it. Okay, you heat it to 90 degree Celsius. Okay, after you heat it, what you did, you drop it in water. Okay, you drop it in water, and this water was initially at a temperature of 20 degrees Celsius. Okay, this was at 90 degrees Celsius. What will happen? There will be heat transfer takes place. Obviously it is at higher we know from thermodynamics law that all what you call bodies try to come into equilibrium state. So when in the equilibrium state, these two will be having the same temperature. So what will happen? The iron bar will lose heat, and whatever heat is lost by the iron bar, it will be gained by the water. Okay, now this is very simple when we apply. Now we will just try to go on from first law of thermodynamics, and again I'm saying you, even if you don't know the first law of thermodynamics, you know that whatever heat is released from this iron bar, it will be absorbed by the water, and that's how they will attain a common temperature. This is what the first law of thermodynamics, but we will go from expressions of the first law of thermodynamics. Okay, so from the first law of thermodynamics, Q is equals to W plus delta U. Okay, now we are considering this water plus iron bar as our system. Okay, now whenever we are considering this as the system, this becomes our boundary. Okay, this becomes our boundary, and I have already told that heat and work are boundary phenomenon. So can you see any heat flowing outside this boundary or coming inside this boundary? No. So that is why the Q exchange is equals to 0. Also there is no any work done on this boundary. Okay, so that is why this work is 0. So that means what? The internal energy change is 0. That is what the expression, and this will lead us to the final equilibrium temperature. Okay, now if you will study more in thermodynamics, you will know that internal energy is a function of temperature only. Okay, and basically for an ideal gas, the internal energy expression U for ideal gas is equals to mCV delta T. Okay, never write Cp for ideal gas, but for solid, liquid and other incompressible substances or fluids, you can write U as either mCp dt or mCv dt. Okay, because the Cp and Cv are not varying much, okay, in case of solids, liquids and other compressible substances. So that's why whether you take here Cp, whether take here Cv, does not matter. Okay, now again the question is giving us Cp, that's why we will take no. It is not telling anything that it is specific heat at constant pressure or specific heat at constant volume. It is only saying specific heats, because both are almost the same. That is why it is only giving the value of specific heat. So that's why it does not express anything. It only says that it is mC delta T. Okay, now then delta U is equals to 0. Delta U is equals to 0 means what? U initial is equals to U final. Now U of what? U of the system. Okay, U of the system. And what is my system? My system is both iron bar plus water. That means initial internal energy of iron and water combined will be equal to final internal energy of iron and water combined. Okay, I'm repeating it again. We have applied the, we already know how we to solve this equation, because we know, but how it came from the first law of thermodynamics, that's what we are dealing in details. Otherwise you can directly, the heat loss by is equals to heat gain. This is a basic 10th level question for you. Okay, so because the system, we have considered the system as both the water and iron bar as the system, and since work is a boundary phenomenon, so the work that is no external work or PDV work or any type of work is felt in this boundary. That's why W is 0, and there is no any heat input, okay, or heat going out from this system through this boundary. That's why this Q is 0. So that's why the change in internal energy is equals to 0. Now when the change in internal energy is equal to 0, the initial internal energy value will be equal to the final internal energy value. Okay, so initial internal energy of the system will be equal to the final internal energy of the system. Let me write this in a new slide. Okay, U initial of the system is equals to U final of the system. Okay, now U initial of the system means U initial of water plus U initial of iron. Okay, similarly U final of water plus U final of my iron. Okay, now what will be the U expression is simply M into C into delta T, or what you can say is that is the change in internal energy, and you can just write it as M into C into T. Okay, you can write as M into C into T. So yeah, now we require the mass. Okay, so mass of the iron is given as we'll calculate this. Okay, so mass of iron, it is given as 50 kg. But what about the mass of water? Okay, so volume of water is given to us. We know the density of water, so we can calculate the mass of water. Okay, so mass is equals to what will be mass? Mass will be equal to rho into V. Okay, we know density 1000. Okay, and I think the volume of the water given to us is 500 liter, so it will be 500 into 10 to the power minus 3. So finally I will get this one as kg. Minus 3 plus 3 goes cancel, so there are 500 kg of water is there. Okay, it's a huge tank. Now yes, now we will put this in this equation. U initial of water is 500. Now specific heat of water is 4.18, so it is kilojoule per kg. I will write everything in kilojoule per kg. And what is the initial T of water? Initial T of water is 20 degrees Celsius. Now there comes a trickier part. Should I convert this into Kelvin, or should I put it in this one? Okay, kilojoule per kg, it should be the unit is wrong, sorry, it should be kilojoule per kg Kelvin, and it should be kilojoule per kg Kelvin. Okay, so this will be, I'm writing this one as same 20. Okay, and what is the mass of iron? 50 into specific heat of iron is given as 0.45, and initial temperature of iron was given as 80. Okay, and then next I can write what this 500 into 4.18 into that T equilibrium, and also I can write as 500 into 50 into 50 into 0.45 into, I can write this one as what I can write this one, I can write this one I can write as T. Yeah, because both of them will attain a final equilibrium temperature as T. Okay, now if you solve this, you will get the answer. Let me solve. Okay, where I have left, yeah. Okay, so can I take anything common? I can take 500 into 1.8. Okay, yeah, so you take this, you will get this one as T into 50 into 0.45 plus 500 into 4.18, and this will be equal to the other side one. Okay, 500 into 4.18 into 20, 500 into 4.18 into 20, 41800, and then next one is what? 50 into 0.45 into 80, 50 into 0.45 into 80, you'll get 1800, 1800. So you'll get final temperature as 41800 plus 1800, and this will be 50 into 0.45 plus 500 into 4.18, and your answer will be 20.63 degrees Celsius. Okay, okay, so let us go to the next question. So water starts boiling in an induction when the base temperature of the utensil reaches 100 degrees Celsius. What is the time required to start the boiling process of water in an aluminum vessel, 1 centimeter thick, base area blah blah blah, and if the initial temperature of the vessel is 20 degrees Celsius? Okay, so suppose you have bought an induction. Okay, so and you keep an utensil here and you will start boiling. Now it is saying that, okay, we all know that water will start boil at 100 degrees Celsius. Okay, but here it is saying that the boiling process starts when this temperature of this base surface, it reaches 100 degrees Celsius. Okay, the utensil temperature of this base utensil, it reaches 100 degrees Celsius. Okay, and yeah, so what is the time required? And this its cross sectional area is given. Yeah, its base area is given to us. This base area is equals to 0.05 meter square. Okay, base area of 0.05 meter square is given, and the thickness, that base area thickness T thickness is given to us as 1 centimeter. Okay, so this much thickness. So okay, from here we can calculate the volume of whatever, and then this is made up of aluminum, it is saying. So density of aluminum must also be given. So density of aluminum is also given to us, and it is 2700 kg per meter cube. So density of aluminum is also given. So from here we can calculate the volume of the aluminum. Now what it is saying, that initial temperature T1 is equal to 20 degree Celsius. Now what you have to do, you have to start the boiling process. When will the boiling process start? The boiling process will start when T2 will be equal to, that is my final, will be equal to 100 degrees Celsius. Okay, so until and unless it reaches 100 degrees Celsius, my boiling process will not start. Now you bought the induction of power 2000 watt, but we know that it cannot be 100% efficient, so there will be some loss of heat due to it may go somewhere else and it may go outside. So it is only 90% efficient. That means what? If 2000, sorry, 90% efficient, that means what? The Q that it can provide to it is actually 2000 into 0.9. so this much amount of rate of heat input it can provide. Okay, this much rate of heating it can provide. 2000 watt you have bought, but it is only 90% efficient, so that's why it can only provide 2000 into 0.9 watt of rate of heat to this. Okay, someone is coming. Okay, yeah, so now this much amount of this is what? Joule per second basically. So I can write this watt as joule per second also. Okay, now what you have to calculate, you have to calculate the time that is required to reach this one. So it is very simple. What will be the heat for heat input for this one? I mean heat required, heat required to reach T2 equal to 100 degrees Celsius for the aluminum is what? Mass of the aluminum, that base area, into Cp of the aluminum, yes or no, into delta T. Okay, now we can calculate the mass of the aluminum. We know density 2700, and we know the volume. Volume is what? Area into thickness, 0.05, this is meter square, and 0.01. so this is my mass. Now Cp of aluminum, is it given? Yeah, specific heat of aluminum is given as joule per kg per degree Celsius, or per Kelvin is same, because we know that delta T it remains the same. So 800, and what is my delta T? My delta T is 80. Okay, so this much amount of heat you require. Okay, 2700 into 0.05 into 0.01 into 800 into 80. Okay, so you require 86400 joule. Now what is your induction that you are buying? It is providing to you 2000 into 0.9. okay, it is providing you 1800 joule per second, just like the first question where we were required to calculate the time. Okay, and we were given the total volume, and we required to calculate the time required, and we were given the volume flow rate. Now in place of that, we are given the total heat that is required to start the boiling process, that is 86400, and we are given the rate of heat flow. Okay, so in 1 second, heat received is equals to what? 1800 joule. Okay, so therefore time required for what amount of heat you require? 86400 joule. 86400 joule will be what? You just apply the unitary method, invert it this one. I think it will be 86400 divided by 1800. You can also put by the unit, it is joule, it is joule per second. Joule will be cut, second will be go above. Okay, so 86400 divided by 1800, your answer is 48 seconds. So within 48 seconds your boiling process will start. Okay, if it is 90% efficient, if it is of 2000 watt, and we know that if we put but remember, it is starting of the boiling process of not the entire quantity of the water. Okay, starting of the boiling process of the what you call water that is available on the near the base, that is touching the base of the metal. If the mass of the water is given to us, then the question would have been a very interesting one, but I don't want to complicate the things. Okay, okay, yeah. So next is, there is a piston cylinder arrangement, and it has 1000 liters of nitrogen gas, and it is at 500 kilopascal and 27 degrees Celsius. Now there is a 220 volt source. An electric current device is connected to pass through a current of 1 ampere for 10 minutes. The expansion process takes place isobarically such that there is a heat loss of 2000 joule during the process. Now what will be the final temperature of nitrogen? Okay, so suppose this is my piston. Okay, this is my piston and this is my cylinder, and it contains nitrogen gas. Okay, it contains nitrogen gas, and the initial state given to us, P1 500 kilopascal, T1 27 degrees Celsius, and V1 is equals to 1000 liter. Okay, now what it is given? Okay, and electric resistance source is connected. Oh, I'm sorry, this you can write this one as also resistance, no issue. Okay, so an electric resistance source is connected, and such that 1 ampere current is flowing through it. Okay, 1 ampere current is flowing through it, and the voltage that is connected to is 220 volt. So such that there is a heat loss, and from this system there is a heat loss. Okay, and then after this what happens, if you heat this up, it will be increasing the internal energy of the system, and that increase in internal energy causes expansion. Okay, this expansion takes place isobarically, that means the pressure remains constant. Okay, so there will be expansion as well as there will be rise in the internal energy, and also there will be a loss of heat to the surrounding. And what is the loss of heat? It is 2000 joule. Okay, so what will be the final temperature of nitrogen? That is our question. Okay, now we will go from the first law of thermodynamics. So Q is equals to W plus neglecting the kinetic and potential energy changes, we already saw what we get this one as Q is equals to W plus delta U. Okay, now what is this W? This W, it contains WPdV plus W electrical plus W pedal work plus blah 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 blah. What we know that this thing is getting expanded, so WPdV will stay. Okay, and there is an electric connection, so W electrical will stay, and rest all we can eliminate because these things are not given to us. Okay, so what we can write this expression as Q is equals to WPdV plus W electrical plus delta U. Okay, this is my one expression. This is from my first law of thermodynamics. Now there is a term called enthalpy. Enthalpy is nothing but it is the sum of internal energy plus flow work. Okay, this is internal energy, you know, this is called flow work. Flow work, it is the product of pressure and volume. Okay, it is called the flow work. So what we can write, if we differentiate this dH, what we will get, du plus p dv plus v dp. Now since this is taking place isobarically, so what we can write, this dp is equals to 0, okay, v dp is equals to 0. So what we can write, dh is equals to du plus p dv. Now remember seeing this one somewhere, yeah. So and again what we know, the expression of w p dv is nothing but p dv, that means integration, plus w electrical plus delta u. Okay, so we are dealing with small amount of dq. I will write this one again so it will be better, so that you will not. So what we can write for small change dq is equals to du plus pdv plus dw electrical. Okay, so and we know that du plus pdv is also equals to dh. So what we can write this one as du plus pdv is equals to dh plus dw electrical. Okay, now we know the, now if we do integration this thing, and remember, okay, I need to put a this sign here. You know why we need to put here? Because this q is a part function and it is an inexact differential. This means what? That q1 to 2 is not equal to q2 minus q1. That's why we cannot write dq as this one. This is wrong. We have to write dq as this one because this is an inexact differential. This is the meaning of inexact differential, that is it depends on the part. Okay, now what we can write is here, then what we should calculate actually, yeah, we should calculate the final temperature. Okay, now then nitrogen, if it is not mentioned you in any of the question, any part, if it is not mentioned, then you can take this whatever gas it is given as an ideal gas. And for an ideal gas, we can write dH is equals to mCp dt. Okay, that is the expression. So we can write dH as mCp dt. Okay, so then what we can write, dq is equals to mCp dt plus dw electrical. Now we should just integrate it. So integration of dq, this will be equal to integration of mCp dt, and this will be integration of dw electrical. Okay, so integration of dq means what? The entire amount of heat that is coming in or going out. Okay, so what it's telling, it is telling that there is a heat loss of 2000 joules. So this is what going out, so that means this is negative of 2000. Okay, now m is what? M is the mass of the ideal gas. Now what is our gas? Our gas is here nitrogen. Okay, so how will we calculate mass? We have P1, we have T1, we have V1. So PV is equals to MRT, and from that we can calculate the mass of nitrogen. Okay, so M is equals to PV by RT. Okay, P1 V1, basically P1 V1 by RT1. So what is my P1? It is 500 into 10 to the power 3 10 to the power 3. What is my V1? V1 is 1000 liter, so 1000 into 10 to the power minus 3, it's basically 1 meter cube. And what is R? We know R is equals to 8.314 divided by molecular mass. Do you know what is the molecular mass of nitrogen? The molecular mass of nitrogen, it's N2. Basically nitrogen, it does not stay as, so this one, the molecular mass of nitrogen gas will be, it will be 14 into 2, it will be 28. Okay, so that means 8.314 by 28, it will be almost equal to 0.296. okay, 0.296, this is kilojoule per kg Kelvin, Okay, So then we are expressing this one as joule, so I will write this one as 296. And what is my temperature? My temperature is 27, so it will be 300. Okay, so this is my mass of nitrogen. The mass of nitrogen is 500 into 1000 divided by 296 into 300. Okay, so 5.63 kg of nitrogen is there. Okay, so this mass will be constant throughout the process, so I can take out from the integration. Cp is constant, I can take out from the integration, and then dt will be nothing but T2 minus T1. Okay, so 5.63, and my Cp value, it is given 1000. Very nice. And I have to calculate T2. I will put it as it is, and I know the value of T1, it will be 27. So since I put in degree Celsius, it will come as a degree Celsius. Now what will be dW electrical? It will be the entire electrical work done. Now electrical work done, how will we calculate? Oh, sorry, draw eraser, yeah. Okay, okay, so to calculate electrical work done, W electrical, we know W electrical is equals to I square into R into T, where T is the time. Okay, I square R into T, but here what it is given, here voltage is given and current is given. So if we express in terms of voltage and current, I think this expression will be V into I into T. Okay, so voltage is 220. How much amount of current is passing? 1 ampere. 1 ampere current is passing, and it is passing for 10 minutes, so 10 into 60 seconds. So your final answer will be in joule. Okay, that will be my electrical work done. 220 into 600. Okay, 132,000. This much amount of work done. So that will be 132,000 joule, 5.63 joule per kg Kelvin. Yeah, let me check the units. You always be careful while checking these units, okay, because that will make you mistakes. Okay, so if I will bring it that side, then it will be negative. Something is wrong here. Okay, so it will be 132,000 plus 2000, 134 divided by, sorry, I will write it in the next one. Okay, this was the W electrical part. So here I have got 13400 negative of 134,123, that is equal to 5.63. Oh, I'm sorry. 5.63 0.6. Okay, I will write this one. 5.63 into 1000 and is equals to T2 minus 27. So what will be my answer? My answer will be T2 will be equal to 27 minus 134,000 divided by 5.63 into 1000. Okay, so these three zeros gone, so 134 by 5.63, 23, so 27 minus, your answer will be 3.198 degrees Celsius. Okay, so this will be the final temperature of the liquid of the nitrogen. Okay, so now okay, so the next one is an ideal monoatomic gas is confined to a cylinder by spring loaded piston, and it is having a cross sectional area. Wait a minute. Okay, it is having a cross sectional area of 8 into 10 to the power minus 3 meter square. Initially the gas is at 300 Kelvin, and it occupies a volume of 2.4 into 10 to the power minus 3 meter cube. The spring is in a relaxed state. The gas is heated by a small heater coil H. The force constant of the spring is 8000 Newton per meter, and the atmospheric pressure is 1 into 10 to the power 5 Pascal. The cylinder and the piston are thermally insulated. The piston and the spring are massless, and there is no friction between the piston and the cylinder. There is no heat loss through the heater coil wire, and the thermal capacity of the heater coil is negligible. With all the above assumptions, if the gas is heated by the heater until the piston moves out slowly by 0.1 meter, you have to find the final temperature. The question looks long, but whenever the question is longer, you will get more and more hints. Okay, we'll go one by one. It is an ideal gas they are telling, and it is a monoatomic gas. What is monoatomic gas? We'll get to know. Okay, don't worry. Yeah, so an ideal monoatomic gas, it's loaded by spring loaded cross sectional area. Okay, confined in a cylinder, spring loaded cross sectional area. Okay, initially the gas is at, so initial condition T1, it is given to me as 300 Kelvin. Okay, and initial volume is given to us as 2.4 into 2.4 into 10 to the power minus 3 meter cube. Okay, initial volume is given. The spring is in a relaxed state. Whenever the spring is in a relaxed state, that means the spring is neither experiencing any source of compression or any source of expansion. Okay, so if this was the condition and this would have been my spring, okay, so initially it is just touching the spring. Okay, these are my gases. Initially it is just touching the spring. Okay, monoatomic gas is placed here. The gas is then after that the gas is heated by a small heating coil. The force constant of this spring is given to us. K is given to us as 8000 Newton per meter, and the atmospheric pressure is 1 into 10 to the power 5 Pascal. Okay, now since initially it is in an what you call that relaxed state, so the pressure will be whatever that is atmospheric, because it is in balance with that one. Okay, so it will be 10 to the power 5 Pascal. So we have got P1, we have got V1, we have got T1. The cylinder and the piston, these are all thermally insulated. That means what? Q is equals to 0. That is, this entire thing is my system, and no heat exchange is taking place between the system and the surrounding. This line states that. Okay, the piston and the spring are massless, and there is no friction. That means there is no heat loss between here to here, and there is no that is what spring dynamics involved in this question. Okay, so this is a very very simple question. And also there is no heat loss through the heater coil. Okay, there is a heater coil that is heating here. Okay, and then there is no heat loss from this heater coil also. Okay, and the thermal capacity of the heater oil is negligible. That means that whatever change in the heater coil is very very negligible in comparison to whatever heat it is getting. Now if the gas is heated by the heater until the piston moves by 0.1 meter, so this piston, it will get displaced x is equals to 0.1 meter. Okay, it will get displaced to upward side, because whenever you will heat it here, it will increase the internal energy and it will push it this side. Okay, so it will be displaced by a distance of 0.1 meter. So if it will be displaced by a distance of 0.1 meter, one thing is clear, because we have a base area, it is given to us. Okay, and we know the initial volume, so we know the final volume. Then the final volume will be initial volume plus uh, initial volume plus area into x. Okay, so my initial volume is 2.4 into 10 to the power minus 3 plus then my what is called area is 8.8 into 10 to the power minus 3, 8 into 10 to the power minus 3, and it is displaced by 0.1 meter. Okay, so I'm sorry, I will not write it here, it's directly meter cube. So my final volume is 2.4 plus 0.8, it's 3.2 into 10 to the power minus 3 meter cube. Okay, so let me check the calculation. 2.4 0.8 2.4 0.3.2 into 10 to the power minus 3. So we know the final volume V2. What we should find? We should find the final temperature. So it is indicating us that if we know now the final pressure, somehow if we know the final pressure, then we will be able to calculate the final temperature. Why? Because we know P1 V1, sorry, we know ideal gas equation PV is equals to nRT. Now in this case, if the number of moles remains the constant and R is always a constant for the same gas, we can write as PV by T is a constant. Okay, so initially we know P1 V1 by T1, so this one we can write as P2 V2 by T2. Now you see here, we already know V1 T1 P1 and we already know P2. We have to find T2. Okay, this one we need to find. If we somehow know what is P2, our question is solved. Okay, so now how will we find P2? P2 is what? In the second state. In the second state, when this spring is getting compressed, okay, the spring got compressed, this got expanded and the spring got compressed. So there was some initial pressure already, that is 10 to the power 5 Pascal. So there will be some additional pressure that will be exerted by the piston, so that pressure will be force by spring divided by area. Okay, so force of the spring, we know, since nothing is given, so we can assume this is a linear string, okay, with the stiffness constant is given to us. Okay, so F spring is equal to my K into X. Okay, so what is my K? My K is 8000. And what is my X? My X is 0.1. So it will be Newton. So it is 800 Newton. So therefore final pressure P2 will be what? 10 to the power 5 plus my that spring exerted pressure, that is 800 divided by whatever was my cross sectional area, that is 8 into 10 to the power minus 3, 8 into 10 to the power minus 3. Okay, so 10 to the power 5, sorry, 10 to the power 5 plus 800 divided by 8 into 10 to the power minus 3. Okay, so it is 2 into 10 to the power 5, 2 into 10 to the power 5 Pascal. So our problem is solved. We know P1, we know V1, we know T1, we know P2, we know V2. Now we can calculate T2. Okay, just put it here. What is P1? P1 is 10 to the power 5. 10 to the power 5. What is my V1? 2.4 into 10 to the power minus 3. And what is my T1? T1 I will be 300. Okay, what is my P2? My P2 is 2 into 10 to the power 5. What is my V2? V2 is 3.2 into 10 to the power minus 3. And what is my T2? I need to calculate. So putting this, what I will get, this 10 to the power minus 3 gone, 10 to the power minus 3 gone, 10 to the power 5 gone, 10 to the power 5 gone. Okay, so it will be 2 into 3.2 into 300 divided by 2.4. So your answer T2 will be equal to 800 Kelvin. Okay. Okay, now let us move to the next question. Okay, a room 4 meter into 5 meter into 7 meter, that means the dimensions of the rooms are given, length, breadth, weight, whatever is given, and it is heated by radiator, steam heating system, blah blah blah. Okay, so the steam radiator transfers a heat at a rate of 10,000 kilojoule per hour, and a 100-watt fan is used to distribute the warm air into the room. The rate of heat loss from the room is estimated to be 5,000 kilojoule per hour. The initial temperature of the room is 10 degrees Celsius. Determine how long will it take for the air temperature to rise to 20 degrees Celsius. Cp of the air is given to us. Cv of the air is also given to us. Okay, so what we know the volume of the room. Okay, so the volume of the room is 4 into 5 into 7, that is 4 into 5 into 7, that is my 20, sorry, 1 4 into okay, fine. So 4 into 5 into 20, it's 140 meter cube. Okay, so volume of the room is constant. Now let us first pictorially see what is happening. This room, it has got some dimensions and there is some heating effect is going on here. I am writing the radiator same as that one, don't get confused. I will, because the heating values are directly given. Then there is a fan, which distributes the that means the fan also does some rotation amount of work. Then there is a rate of heat loss. Okay, and then initial temperature is given, T1 is given to us, and we T2 is also given to us. We have to determine what is the time taken to go from T1 to T2. Okay, so this is the volume given to us. It is containing what it is containing. I think it is containing nothing is given, that means Cp of air is given. This room has containing air, so the mass of the air we need to calculate basically. Okay, so the initial temperature of the room T1 is given to us 10 degree Celsius. We can convert this into 283 Kelvin. I'm sure you people know how to convert from degree Celsius to Kelvin. Okay, and T2, it is 20 degrees Celsius, so it will be 293 Kelvin. Okay, now yes, okay, now what okay, so first let us apply the first law of thermodynamics. Q is equals to W plus delta U. Now since it is air, nothing is told to us. Until and unless nothing is told to us, every gas that is given is an ideal gas, and for an ideal gas the change in internal energy is mCv delta T. Okay, but remember here heat loss is given in terms of rate. Okay, heat loss is given in terms of rate. So if we convert this equation into rate, that means it will be dq by dt, we'll just differentiate with respect to time, dw by dt plus delta u by delta t, I can write. Okay, so then this will be what, q dot, and this will be what, w dot, and this will be nothing but delta u by delta t. Okay, now q dot is what, that the rate of heat loss from the room. Okay, so q dot is equals to 5,000 kilojoule per hour. The question is very simple, you just have to make sure the units are same. And what is w dot actually? W dot is the nothing but the work, and this consists of what, it consists of W dot fan, okay, and it also consists of the radiator, okay, W dot radiator, okay. So W dot fan, it is doing work on the system, so it is minus 100. Fan is given in terms of watt, and radiator it is doing work on the system, okay, so it is also doing 10,000 kilojoule per hour, okay. W dot, yeah, it's correct. So we need to express everything in terms of watt. So if you express this one in terms of watt, it will be 5,000 into 1,000 divided by 3600 watt, and this one will be minus 100 minus 10,000 into 1,000 by 3600. Everything's in watt, okay. And here we will put, and we'll get the final expression as in time, in seconds, okay. So yeah, let us put again 5,000 into 1,000 by 3600 is equals to wait a minute, the steam radiator transfers the heat rate of this one, and 100 fan is okay. And this one, what we can write is this one we can write as minus 100, and this one I can write this one as minus 10,000 into 1,000 divided by 3600 plus mcv T2 minus T1.
Excuse me, sir.
Yeah.
This 5,000 kilojoule which you had taken on the left hand side, it should be negative, na? With
Yeah.
negative sign,
It should be, yeah. Thank you. That's why I think, yeah. It's loss. Yeah. Thank you. Okay. Thank you very much. So mcv into T2 minus T1 divided by delta T, okay. So put it here, everyone, you will get, it will be a messy calculation, I know, but bear with me. Okay, let me summarize something. Am I missing some term? Have we calculated the mass? No, we have not calculated the mass yet. So we can calculate the mass from P1 V1 by R T1, okay. Now if you have attended the classes, I think this has come to your part. For an ideal gas, your Cp minus Cv is equals to R, okay. And you can also calculate for air also. The values will not be too much of different, because air is consisting of nitrogen and oxygen only, and the molecular mass of air is almost 28, it becomes, and so, and from there also you can calculate. But here, since Cp and Cv values are given, so we will just subtract it, and we will get the values of, we will get the value of R, okay. So the R will be 1001 minus 718, so it will be 283 joule per kg Kelvin, okay. So my pressure is given, is it given my initial pressure? Oh, it is not given initial pressure, but since it is a room, what we can tell, we can take the atmospheric pressure, okay. There are some terminologies which will be hidden. Suppose that it is telling about a room, okay, and there is air here, so it is by default it is the atmospheric air pressure. So my P1 will be 1 that is bar, that is 10 to the power 5 Pascal. My V1 I have already taken, that is, it remains constant, so that will be 140, okay. And my R value I have taken this one 283, and my initial temperature, it is 283. Oh, it came same. Oh, it can come same, no issue. So it is 283, so that will give you 10 to the power 5 into 140 divided by 283 into 283, Okay, so 174.80 kg. Now put it here. You know CV, you know T2, you know T1, and from here you can calculate delta T. Okay, let me make this 1 minus 1388.88 minus plus 100 plus 1000, 10,000 into 1000, 277.78, and that will be equal to M174.80, CV 718, I think. Yeah, CV value is given as 718. T2 minus T1 we can directly write as 10 degrees Celsius divided by delta T. Okay, so 277.78 plus 100 minus 1388.88, okay, 1488.9, and this will be your 174.80 into 7180 by 1, so 1.25 into 10 to the power 6 by delta T. So from here your delta T will be 1488.9, 842 seconds almost. Okay, now let us move to this question. A massless piston which can move, how many questions left? I think this is the last second question. Okay, a massless piston which can move without friction closes a sample of helium in a vertical thermally insulated cylinder which is closed at its bottom, and the cross section of which is 2 area is equals to 2 dm square. Dm, you know, I think it is decimeter. Okay, now above the piston there is a fixed stand to which an unstretched spring of springs constant 2000 Newton per meter is attached, whose bottom end is at a distance of 2 decimeter from the piston. Okay, and when the volume of the gas is V0 is equals to 8 decimeter cube. The external pressure P0 is equals to 10 to the power 5 Pascal, and your G value is given as 10 meter per second square. The gas confined in the cylinder is heated with an electric heating element. Okay, this is the unit conversion is also given, so you should not think about it. How much heat is supplied by the element till it reaches the spring? Okay, this is a very interesting question. Now you supply heat to it, it will increase the internal energy, it will expand, and it will go and it will just touch it here. Okay, and we just have to calculate the heat that is required for the piston to just touch the spring. We are not at all concerned what will happen after that in compression and after that. Okay, so we are just concerned about how much heat you should supply from this heater, so that it will go from this point. Let us suppose this is point O, this is point A, this is point B. So how much it is required to go from point A to point B. Okay. Okay, so what are the things that are given to us? K is given to us as 2000 Newton per meter square. 2000 Newton per meter, and area is given to us 2 decimeter square. 2 decimeter square, that is equals to 2 into 10 to the power minus 2 meter square, and how much we will have to displace? We will have to displace by a distance of 2 decimeter, because this distance is equals to 2 decimeter. Okay, so we have to displace x is equals to 2 into 10 to the power minus 1 meter. I am directly converting it. Okay, 2 decimeter is given, and our initial volume here V0 is equals to 8 into 10 to the power minus 3 meter cube. Okay, so this much is given, and our initial pressure P naught is equals to 10 to the power 5 Pascal. Oh, I'm sorry. Okay, initial pressure P naught is that, because since external pressure is P naught is equals to 10 to the power 5 Pascal, and until it touches the spring, it goes as what we call quasi statically, and it at each and every step it will experience a constant pressure. That's why it's after touching the spring, its pressure will change linearly, or it depends on the spring type, but we are only concerned till the touching of the spring. So that's why that P naught value, that is equals to our 10 to the power 5 Pascal. Now and again G is we know that G we should not write. Now what is the work done in order to go from O to A? Okay, in order to go from O to A. Now what is it? This is a constant pressure process. Okay, so work done, it is a constant pressure process. So what will be? It will be nothing but W is equals to P dV integration. So that will be P naught, that basically P naught into whatever area into X. That's it. Okay, so P naught is my 10 to the power 5. Okay, my area is 2 into 10 to the power minus 2, and my X is 0.2. okay, so that is equal to 400 joule. Okay, so 400 joule. Now what we require heat. Okay, so we require heat. What is the heat that it will give to us? Okay, now let us come to the ideal gas equation, because here helium is there, it is a gas, and it is not saying that it is not an ideal gas, it is a real gas, so we'll always take this one as an ideal gas. So we know that PV is equals to mRT. So what we can write is as I'm differentiating both sides. This will be equal to D of mRT. So this will give you P dV plus V dP is equal to m is constant, r is constant, so it will be mr delta T. Okay, so constant pressure process, so this will be equal to 0. So that means what? My P dV is equal to mr delta T. Okay, P dV is equals to mr delta T. So that means okay, mr delta T. Now heat. Now see what is the amount of heat and how it is being added, since it is a constant pressure process. So in a constant pressure process, for a constant pressure process, heat added is equal to Q is equal to, can we write this one as m into Cp into delta T? Yes, we can, because this is a constant pressure process and it's valid for everything. Okay, so now from here, okay, now again, yeah, so from here can we express, since we already know the value of P into dV. Okay, so this is already, we have P dV value, we have already there. So what we can do is that m into delta T is equals to P dV by R. Okay, so that means we have got this one. Now our main task is Cp, because if in the question helium's Cp value was given, then it is already good, but you will get a formula. I actually forgot what was the formula. I think it was Cp is equals to n by 2 plus 1 into R. Okay, for any gas where n is the number of degree of freedom, okay. So for helium, since it is a what you call diatomic gas, so its degree of freedom it is, I think, its degree of freedom is 3, so it will be Cp value for helium is Cp of helium, it is 5 by 2 times R. Okay, so it is 5 by 2 times R. You put it here, what you will get, Q is equals to M into delta T into Cp. M into delta T you put it as P dV by R. Okay, and Cp you put it as 5 by 2 times R. So R value got cancelled, so that means this is nothing but 5 by 2 times whatever PdV work you have got. So the PdV work you have got was 400. Okay, so your will be 200. Okay, so your answer is 1000 joule. Okay. Okay, let us come to the final question of today's session. Okay, so here question is given, air in a tank is at 1 megapascal and the room temperature.
भाई बंदा मालूम है आया 68 से 10 क्वेश्चन लगवा दिए.
Sorry, hello. Air in a tank is at 1 megapascal and room temperature of that is at 20 degrees Celsius. Now it is used to fill an initially empty balloon to a pressure of 200 kilopascal, at which point the diameter is 2 meter and the temperature is 20 degrees Celsius. Assume the pressure in the balloon is linearly proportional to its diameter and that the air inside the tank can you please mute yourself? Yeah, so air in a tank is at 1 megapascal and the room temperature and it's 20 degrees Celsius. So it is used to fill an initially empty balloon to a pressure of 200 kilopascal, at which the diameter of the balloon will become 2 meter and the temperature will also be 20 degrees Celsius. That means that inflation of the balloon, it is taking at a constant pressure process, constant temperature process, and the temperature is not at all changing. Now assume the pressure in the balloon is linearly proportional to its diameter and that air in the tank also remains at 20 degrees Celsius throughout the process. Now then you have to find the mass of the air in the balloon when it is filled, and then also you have to find the minimum required volume of the tank. Okay, so from a tank you have to fill a balloon from its empty to a diameter of 2 meters such that it attains a diameter of 2 meter. So here we will take two assumptions. First assumption is that we already know that air is ideal gas, we will take because nothing is told about the type of gas, so air is ideal gas. And second one, the balloon, we know that the balloon normally it can take any type of shape. I mean we have seen so many types of balloon nowadays, it can take different types, but we will take that the balloon takes a spherical shape. Whenever you are doing this, the shape of the balloon, spherical balloon. Okay, whenever you are filling it up, it takes the shape of a sphere. Okay, so then what will be the final state volume? So let me take out the balloon final state. Okay, so balloon final state. So in the final state, the balloon's volume V2 will be 4 by 3 pi R cube. Okay, so what will be the answer then? 4 by 3 pi into 1 cube, because the diameter of the balloon is given as 2 meter, so its radius is 1. So what will be it? 4 by 3 into pi. Okay, so 4.18 meter cube. So that is my final state of my balloon. Then you have to calculate the mass of the air in the balloon at the final state. So at the final state, what else we know? Do we know the density? No. If we have known the density, see, if nothing is given, you don't take the density of air as 1 because it consists of many other things, so you have to go by other way. So what we can do, we can apply ideal gas equation in the second state and then we can calculate the mass. do we know the temperature at this is the balloon filling state. Do we know the temperature? Yeah, I think we know the temperature is same 20 degrees Celsius, so it will be 293 Kelvin. Okay, what we require P. So P2 of the balloon, I mean in the final state the balloon's pressure, yeah, it is filled to a pressure of 200 kilopascal is given. So P2 is 200 into 10 to the power 3 Pascal. Okay, so and R is given to you. Okay, so what we can do, P2 V2 is equals to M R T2, and from here we can calculate the mass of the balloon, mass of the air in the balloon basically. Okay, M2 we can write as balloon, because in the next step we have to use this part also. Okay, so P2 is 200 into 10 to the power 3 into V2 is my 4.18, and my R is what is my R? It's kilojoule, no? We can convert it into joule, 287, and T2 is my 293. Okay, so 200 into 10 to the power 3 into 4.18 by 287 into 293. So your final in mass of the air in the balloon, it will be 9.94 kg. Okay, 9.94 kg will be there in this. So this first part is about the mass of the balloon in the the mass of the air in the balloon. It will be 9.94 kg. Okay. So next is what we have to calculate what is the minimum required volume of the tank. So this process it will, I mean what minimum volume of the tank it should be, so that the balloon will state this the balloon will reach this final state. That means you have to fill the balloon to a diameter of 2 meter to a pressure of 200 kilopascal. What minimum amount of air you require to have inside your tank? Okay, that is your question. Now since final pressure of balloon is 200 kilopascal. Okay, so the final pressure of balloon is 200 kilopascal. What will happen, that therefore in the final state pressure of the air inside the tank that should be greater than or equal to 200 kilopascal, because from the tank the air is flowing inside the balloon. So in the final state, if there is maintaining a pressure of 200 kilopascal, so air is flowing from the tank to the balloon, so the tank should have a minimum pressure of 200 kilopascal. Okay, so therefore mathematically what we can write, that second state the pressure of the tank it should be greater or equal to 200 kilopascal. Okay, now then mass of the tank, I mean mass of the air inside the tank, okay, in the second state it should be greater than or equal to P2 into V of tank, that is the volume of the tank, by R into T2. Remember this T2 for the tank and for the balloon is the same. This P2 is this P2. Okay, now if I will consider my initial mass of air in the tank is m1. Okay, I am assuming my initial mass of air inside the tank is m1. Now can I write my m1 is equal to m2 of balloon, because it is filling the balloon, and at the same time M2 of the tank. Initially M1 was there, out of which M2 mass is used to fill the balloon, and the remaining M2 is inside the tank. Okay, so M1 state, can I write this one as P1 V tank, because the volume of the tank will remain the same, P1 V tank by RT1, and M2 of the balloon we already know, its value was 9.94, and this one we can write as P2 V tank by RT2. Okay, so V of tank is common, and we know that T1 and T2 are the same, so we can directly write this one as P1 V tank is equals to 9.94 into R into T is equals to P2 V tank. Okay, so from here if we take V tank common, what we will get? P1 minus P2, and this will be equal to 9.94 into R into T. So from here V of tank will be equal to 9.94 into R into T divided by P1 minus P2. Now let us check, do we have all these things? P1 is given to us of the tank 1 megapascal. P2 of the tank, it should be minimum, because it is asking a minimum volume now, so we can take P2 as 200 so that we can calculate the minimum volume inside the tank. So we will take P2 as 200 kilopascal. Okay, we need to calculate the minimum one, so we have P1 is equal to 1 megapascal, and we have P2 as what was P2 is it is as 200 kilopascal, 200 kilopascal, and we have the value of R. Yes, we have the value of R. R is 0.287 kilojoule per kg Kelvin. Okay, and do we need anything else? R we know, and do we know T? Yes, we know T. T is the same, that is 20 degrees Celsius, and that is equals to 293 Kelvin. Okay, so we'll put it here in this expression. V of tank, V of tank, it will be equal to 9.94. I'm converting everything to joule per kg Kelvin, so it will be 287. R into T, T is 293, and P1 minus P2. So P1 is how much? 1 megapascal, so I will convert it into pascal, 10 to the power 6 pascal minus 200, that means 2 into 10 to the power 5 pascal. Okay, so this will give you the final answer. So it will be 9.94, sorry, 0.94 into 287 into 293 divided by 10 to the power 6 minus 2 into 10 to the power 5. So 1.044 meter cube. So this much minimum amount of air should be there inside the tank in the initial state, so that your balloon can expand to have a diameter of 2 meter, and whatever the conditions are there. So thank you everyone for attending to this class. So we'll meet next Tuesday. If you have any doubt, you can ask me.
Thank you, sir. Really, it was very good explanation, sir, for all the problems.
You can were you able to access my lectures in that link I have uploaded?
Okay. So, sir, you have uploaded those lectures in in the same thermodynamics that week 1 and week 2, like that one?
Yeah, since there are two TS, Avik will be uploading, and in the same time there will be two link will be there for both the presentation as well as your video. So you go through it and you will get two links. He will be doing some questions might be similar, but some of the questions are different from me, because you cannot find so many different questions, because since you are in the beginning stage. Okay.
Okay.
And in case you have any doubt, you can see in the first slide itself I always give my contact details. In case you have any doubt, you can just mail me here. Okay, I will be available and I can reply to you. Okay.
Okay. So here is okay on this particular email address.
Yeah, you can mail me if you have any doubt, like you can't access these things, or
Okay.
you are not able to understand these things. Okay.
Okay.
But
Okay.
we cannot directly solve your assignment questions. There is a limitation, that's why we are not solving. Okay. But we are trying to solve questions such that you will be able to do the questions properly. Okay.
Yeah, definitely. Sir, one thing just I want to ask that if these are the assignments, so I have submitted all the assignments. So later on, there will be some discussion on the assignment.
Basically it depends on the whatever TA that is assigned in the institute. Okay, that
Okay.
IIT Delhi, you can ask that faculty who is taking the course. Okay, about the
Okay.
assignment discussion. We are
Okay.
not supposed to discuss, I think, that assignments. We are only supposed
Okay.
to do numericals that will be helpful for solving the assignments, as well as for gate related questions you can solve. Okay.
Okay. Okay. Thank
Okay.
you, sir.
Okay,
Thank you.
thank you very much.